In this video, we're going to solve one practice question on capital budgeting. Question number 3 from chapter 12. So I have the question here. In this question, we have a list of 6 alternatives, 6 projects. We know their net present value, which is basically the equivalent value of the project at the current time, the equivalent value of the cash flows of the project, all the revenues, the present value of all the revenues minus the present value of all the costs of the project. So we do have all these numbers. And also for the next 3 years, we know exactly how much capital we need for each project. So let's say for project 1, which is the limited warehouse expansion, we know that if we decide to undertake this project, we need to spend $3,000 of capital in year 1, $1,000 of capital in year 2, $4,000 of capital in year 3. So we do have all these capital requirements and NPVs for all these 6 projects. And also, we know exactly how much capital we are going to have available for each year, during each year. So for year 1, we have $10,500, $7,000 at year 2, and $8,750 at year 3. So these are the capital funds that are available, that are going to be available in each year for the next 3 years. So in part A, develop and solve an integer programming model for maximizing the net present value. So this is a capital budgeting type of problem. The values of investment, the dollar value of investment are fixed. You're not gonna increase or decrease the amount. You're not gonna decide about how much money you're gonna actually put there on each one of these projects. The decision that you have to make is whether or not to pick them, whether or not to invest in each one of them. All right, so it's going to be a pure binary type of problem, and we have 6 alternatives: limited warehouse expansion, extensive warehouse expansion, test market new product, advertising campaign, basic research, and purchasing new equipment. So 6 decisions, 6 alternatives, 6 decisions, 6 binary decisions. So I'm just going to start with the formulation of my model. So decision variables. So we're going to first formulate it, all the parts, part A, B, and C, and then we're going to solve them. Decision variables, whether or not to invest in project I. And I'm just going to give them a number. So 1, 2, 3, 4, 5, 6. And I'm going to call them XI. And XI is going to be 0. XI is going to be 1 if invested, and 0 if not. So it's going to be a binary type of variable, binary type of decision variable, right? So that's my decision variable. Next, so I have 6 of them, right? So 6 projects, 6 decision variables. Next, objective function. We want to, which we want to maximize here. We want to maximize the net present value. Objective function, we want to maximize net present value, actually sum of net present values of the projects that we decide to invest at the end of the day. So it's going to be 4,000, and I'm actually going to factor all the numbers in both objective function and the constraint. by 1,000. I'm going to divide all these numbers by 1,000, and I'm going to present all these numbers instead of $1 and $1,000. So my NPV is going to be $4,000 if I pick project 1. So 4 times X1. So if X1 is going to be 0, if X1 happens to be 0, if I don't invest in project 1, then I won't get this NPV. It's going to be 0. 4 times 0, 0. If X1, the decision regarding the first project, is 1, meaning that I invest in that project, then 4 times 1 is going to be 4. So I would get that for 4,000 actually. So 4 times x1 plus 6 times x2, 6 times x2 plus 10.5 x3 plus ... 4 times x4 plus 8 times x5 plus 3 times x6. But I'm just gonna it's simple, right? So you got the idea. It's going to be net present value of each project multiplied by the decision regarding that investment, yes or no type of binary type of decision variable, which is going to be binary 0 or 1. So that's the objective function. The typical uh, type of constraints that we have to have for capital requirement is the capital availability, the capital fund availability or capital fund requirement constraints for each year. So I'm going to write down. So that's the answer to part A of this question. So this is subject to we have 3 years, year 1, year 2, year 3. And at each year, the amount of capital that we use should be less than or equal to 10,000, should be less than or equal to the capital available at each year. So for year 1, it's going to be 3 times x1 plus 2.5 x2 plus 6 times x3 plus, again, I put ... should be less than or equal to. So 3 times x1 plus 2.5 times x2 plus 6 times x3 plus 2 times x4 plus 5 times x5 plus 1,000 or 1 times x6 should be less than or equal to 10.5. And it's very important, if you're dividing these numbers by 1,000, you have to make sure that you're doing it for both right-hand sides and left-hand side, the coefficient at the left-hand side and the right-hand side, all right? So that's the constraints, that's the capital budget constraints for year 1. It's the same thing for year 2, 1,000 for X1, project 1, 3.5 thousand for project 2, plus 4,000 for project 3, ... less than or equal to 7,000. For year 3, 4 times x1 plus 3.5 times x2 plus 5 times x3 plus ... less than or equal to 8.75,000, right? 8.75. All right, so that's the constraints. And then xi's, we already defined it here, but let me just write it down again. 0 or 1, they can only be 0 or 1 binary type of variables. All right, so that's the answer. That's almost the answer to part A. We just developed the model. We haven't solved it. So I'm gonna actually develop a spreadsheet model right below this. But before that, let me just answer, or at least let me just formulate the answer to part B of the question. So for part B says, assume that only, like I said, we're not done with part A. I'm gonna go ahead and create a spreadsheet model and solve for part A, the model that we formulated. But before that, let me formulate the constraints for part B and C. So for part B says, assume that only one of the warehouse expansion project can be implemented. Only one of these two, X1 and X2, only one of them can be one. Modify your model from part A. So we now have an additional constraint. So out of X1 and X2, project 1 and project 2, activity 1 and activity 2, we can only pick one of them. So these are mutually exclusive, these two, right? And we know that for mutually exclusive type of constraints, we have to have some of those binary decision variables less than or equal to 1. When we can pick at most 1 out of a list of projects, that means we have to make sure that the sum of these 2 or k or whatever number of constraints that you're considering, whatever number of variables that you're considering, to be less than or equal to 1, meaning that only one of them can take 1, or both of them should be 0, right? But they can't be 1 at the same time. So it doesn't allow this to be, this sum to be 2. That's what this does. And then part C, suppose that if test marketing of the new product is carried out, the advertising campaign also must be conducted. Modify your formulation from part B to reflect this new situation. So modify your model from part B. So part B is actually all the formulation that we had in part A plus this new constraint, right? But I just wrote the new added constraint. And for part C, I'm gonna again do exactly the same thing, the new constraints that we have to have. So here we have a conditional type of constraint. So if test marketing is selected, advertising campaign must also must be conducted. This means that test marketing of the new product is conditional on the campaign, the advertising campaign. So test marketing is X3. Let me just write it down. X3 is conditional on X3 on advertising, X3 and X4. So let me write down this and see if this works. X3, if X4 is conducted, if X3, if the test marketing, which is 3, if that is conducted, it means 4 has to be conducted. All right. So now if X3 wants to be 1, X4 has to be 1. So this will make sure that that happens. But if X3 is 0, X4 can be either 0 or 1, right? So this constraint, this conditional constraint will make sure that actually, like it's again similar to phase 2 and phase 1 of a project. Phase 2, the decision variable for phase 2 should be less than or equal to the decision variable for phase 1 of a project. So this is the main one, the advertising campaign. That's the main one, and the one that is conditional on that would be the second one, which comes here to the left-hand side of the condition. So having said that and having all these constraints, let me go ahead and create this spreadsheet model. I have the list of parameters, list of all these coefficients. So the decision variables, decision whether invest or not. So I have six alternatives, 6 decisions to make. All right, one for each one. Limited warehouse expansion all the way to purchasing new equipment. All right, so one for each one. Let me just bring this down. So that's my decision variable. And this is set of decision variables. Objective function is going to be the NPV. NPV is multiplied by decision variables, sum product actually. So the objective function, which is the NPV, which we want to maximize, is going to be, I'm just going to write it here. It's going to be sum product of the NPVs and decision variables. So 4,000 times whether or not we're going to invest, right? If this is 0, it's going to be the multiplication is going to lead to 0. If this is 1, at the end of the day, after we find the optimal solution, if this is 1 times 4,000 is going to be the net present value of 4,000 is going to be realized. So that's the formula that I'm using for the objective function. And now the set of constraints, I had 3 constraints in my part A. In the formulation for part A, we had 1 for each year. And I'm going to write them down here. So let me just copy year 1, year 2, year 3. So the capital needed or capital required for different projects in year 1 is going to be sum product of the capital requirement at year 1 with multiplied with the decision variables regarding the investment. All right, so sum product of the capitals needed in year 1 multiplied by the decision, the binary decision regarding each one of them, right? The corresponding decision variable. So that's for year 1, except that I'm going to fix my decision variables because I'm going to copy the formula. So I'm going to fix that by adding the $sign, by adding the F4, by pressing on F4 on your Windows keyboard. And that has to be less than or equal to the available capital budget at year 1. All right. So, and then we can simply drag it to the right. Let me just maybe write down or show you the formula that I had for my first cell here. So for year 1, this is my formula. Sum product of the capital budget requirement at year 1 multiplied by the decisions that has to be less than or equal to the capital funds available at year 1. And then for year 3 is going to be capital requirement and year 3 multiplied by the decision variables that has to be less than or equal to 8,750. All right. Yeah. So, and it's okay. Again, I'm in my spreadsheet model, I'm using thousands, numbers are in thousands, but in my formulation, when I wrote it down, I just wrote my numbers in thousands. It's not going to affect anything because Objective function coefficients, actually, when you multiply them by a constant number, when you multiply all of them by a constant number, it's not going to change anything. Absolutely nothing is going to be changed. On your constraints, if you multiply both left-hand sides and right-hand sides, again, nothing is going to be changed in terms of your final solution, in terms of your optimal solution. So what I'm going to do now, I'm going to solve this, and this will be the answer to part A of my question. So solver, I want to maximize the objective function, and the objective function is right here, J28. We want to maximize this. We want to maximize it. Maximize this one. This is the net present value by changing this these 6 decision variables and subject to the yearly capital requirement. So the amount needed should be less than or equal to the amount available for each year. So that's it. And one more thing, I'm just going to add it right now, the binary constraints. All my decision variables in this example are to be defined as binary decision variables. Okay. Solving method, make sure to change it to simplex LP. So binary constraints, the capital requirement constraints, decision variables, 6 of them, and maximize the net present value. So that's all I need for, that's all that I need for part A of these questions. So when you solve it, this is going to be your optimal answer. So 17,500 in NPV, total NPV, and you're going to invest in test marketing, new product and advertising campaign, and also purchasing new equipment. But you're not investing in warehouse expansion in either form, limited or extensive. You're not investing in basic research. And you are, all the capital requirement constraints are satisfied, definitely, and all of them have some slack. None of them are binding in this case. So, and then, so this is the answer to part A of this question. You can just copy and paste it over here. For part B and C, you can add them one by one, add these 2 constraints to your solver and solve them again. But let me just check. So we had the mutually exclusive constraint where it says x1 and x2 should be less than or equal to 1. That is actually satisfied. So by not investing in any of those, we're good. Part B, the constraints for mutually exclusive, is already satisfied. But you can definitely add that to your, let me just add that and solve it again. It's not going to change anything. Add sum of x1 and x2. Oh, wait, let me just add it here. So part B constraint, part B, the left-hand side, sum of x1 and x2. Should be less than or equal to 1. I just typed 1 and all right, so that's the part B. For part C, I have actually x3 less than or equal to x4 equals x4. Let me show you the formula. F29 less than or equal to F30. 30. All right. So here I have, so that's for part, the constraints for part B and the constraints for part C. And if you add those to your solver, nothing is going to be changed because, like I said, both of them are already satisfied. You can check it right here. So both of them are satisfied. So nothing is going to be changed. But if you just want to make sure that you have them on your solver, I'm going to add them together right here. So add for part B, and then add for part C. Okay. And then, like I said, if you solve it, it's not going to change anything because these constraints are not binding. These constraints are not actually restrictive. These are already satisfied in terms of your current optimal solution.